I want to tell you is that I forgot to upload the programming assignment, okay, number 2, last week. So I'm going to do it today, okay. I'm very sorry. Of course, I'm going to extend the deadline, okay. And another thing is that, okay, there will be, I believe it's like the 教务处 or like 教育部, okay, they are going to investigate the learning efficiency between the course that is taught in English and the course taught in Chinese, okay, 就是说他们要评估说那个英语教学的就是效果，因为有一些课是有一个 session 是英语的，有一个 session 是那个中文的，就像 like our class, okay, algorithm, okay, one session is in Chinese, our session is in English, so they are going to evaluate like how well you guys learn the subject, okay. So they are coming I think they are coming on 11 a.m. okay, to do a survey, okay. 就他们11点钟会过来给你们一个问卷哦。那 yeah, just for your information, okay. But it will not affect me. It will not affect my teaching anyway, okay. So that's the second thing, okay. The last thing, okay, is that, okay, once at the end of last lecture, okay, a student came to me saying like the 17th week is actually which week? 17th week, it's actually like the first week of the June, okay, is I forgot. But anyway, last time I announced like the date for the final and the programming exam, okay. A student came to me saying like, okay, so this is different from what I announced like at the beginning of the class. I believe like at the beginning of class I announced like this class will be 17 weeks. Okay, so I believe like 所以第17周是哪一个礼拜 ？The second week of June, right? 是 June 的第2个礼拜，对不对 ？Yeah, so here's what we are going to do is like the originally which date I told you for the final. 一开始我上堂课我告诉你们是几月几号开那个期末考，6月4号，6月4号。Yeah, so so the final I believe 6月4号是第16周，对不对 ？Okay, so the final will be a week later. Okay, not June 4th, okay, it's going to be June 11th, okay, and the programming exam is also going to be a week later. It's going to be the Tuesday of the following week, but however, this brings a question, okay, because like I announced that like in E class about these dates, and a student came to me saying like, okay, he's like a senior student and he's graduating, so he has some personal arrangement, on the 18th week， 他第18周他就不在台湾了。So but for that, okay, because what should I say? Like I prefer not to put the programming assignment and the programming exam and the final exam in the same week. Okay, but because he's not going to be in Taiwan in the 18th week, okay, 他第18周不在台湾。So to be fair to that student, okay, I'm asking you， 我要问你们 ，OK， 就是说你们觉得说第17周考期末考跟考那个上机考一起放在第17周，你们是 OK 的吗？还是你们 prefer 第17周期末考，第18周上机考？我要先问你们。Because like that's only one student that has the problem, right? If all you have no problem to move like these two exams in the same week, then we will do it this way, okay? At the same time, we can accommodate his request, okay? 就是我们如果说大家都觉得 OK， 我们就可以就是算作帮助到他嘛，就是把它放在同个礼拜。However, if most of you disagree with this arrangement, then I would just tell him that I'm sorry, like because this is most of the students prefer, you know, to do it like 第17周期末考，第18周考上机。所以就是我们都民主国家嘛，所以问大家，你们觉得说哪一个比较好？还是都没有意见？没意见就是当做好哦，就是可以放在同个礼拜哦。好，你们觉得说可以放在同个礼拜的，举一下手。一个、2个、3个，所以有4个，有4个学生觉得说，如果说要把它放在第17周放期末考，第18周放考程式的，举一下手。1个、2个、3个、4个、5个、6个。好像那其他的没有举手，我们这边应该超过10个学生吧？我刚刚有讲哦，完全没有举手，代表说 OK 哦。你们确定哦？我这样讲的意思是说，6票是赞成分开考的，那其他没有举手跟举手可以同个时间考的，都是代表同个时间、同个礼拜考哦。你们确定哦？如果大家 OK， 因为这样子看起来，你们我再问一次，我反过来问好了 ，OK， 不就是赞成分开成2个礼拜的考的，举一下手。不好意思哦，因为这个影响比较大，1个、2个、3个、4个、5个、6个、7个，现在7票。所以说，其他的人是觉得说可以放在同个礼拜考的，对不对？好，我再问一次，同个礼拜考的举一下手。这只有2 binary 哦，没有说超1、2、3、4、5、6、7、8、9，对，的确是好，至少。有比较多的人愿意举手。如果说按照这样子，那我们就放在同个礼拜考哦，大家可以接受哦。就是说我知道说有些人觉得还是 prefer 分开2个礼拜。我自己 ，OK，I myself feels that if we put them in different weeks, it may help you, okay, better prepare. But if most of you feel like it doesn't matter.We will do it this way, OK？ 就是我们就放他们这2个考试在同个礼拜，好不好？就是我当然这样子有另外一个好处是，第17个礼拜就把它都干掉了，第18个礼拜你们就放暑假，对不对？对，那我觉得也很好。 就是对我来讲没有影响，但是我是就是说确定说你们是觉得这样 OK， 好不好 ？OK， 对，好，所以就是 Let me repeat 哦，the final exam is going to be June 11th， OK， 就是那个第17周的礼拜3 ，and the programming exam is going to be on June 10th， 就是第17周的礼拜2 ，OK， 根据刚刚投票的结果，好不好 ？OK， 虽然说差距并不大啦，可是well， 就that's the result，OK。Okay, and so last time we finished amortized analysis, right? Okay, so I actually there is a 14th lecture, but I think like okay， 如果我们期末考试6月11号，那我们大概还有4次上课时间，对不对？连这一次有4次上课时间。So I prefer to finish like some important topics, such as like dynamic programming, greedy algorithm, as well as some graph algorithms, such as like min-max flow. Okay, and if possible, NP complete. Okay, so the following lecture I'm going to jump. Okay, between two different lectures. Okay, just want you to be aware. Okay, so the first one is going to be dynamic programming. Okay, which, by the way, is perhaps like one of the most important subjects in algorithm, okay? And this is also something that you may not have learned previously, okay? Because in data structure, obviously, you will not, usually the lecture will not cover dynamic programming, okay? And we are going to use one interesting example to show you how dynamic programming is conducted. Okay. So the dynamic programming design technique, it's kind of like divide and conquer, but it is more efficient than divide and conquer. Okay, I will get to that point later. Okay, but it's perhaps the good timing to introduce this example. This example is kind of famous. Okay, it's like many textbooks use this example to talk about dynamic programming. Okay. Back to when I was like a math undergraduate student, okay? Of course, I also learned dynamic programming, but at that time there is no common, 你没有那本很厚的教科书哦。那 okay, but even at that time, okay, we used the LCS, okay, this problem to talk about dynamic programming. Okay. So what is this problem? It's like this. Given two sequences, okay, which are represented as X and Y, okay, these two sequences may or may not have the same length, okay? So X is of size M, Y is of size N, and M and N may or may not be the same, okay? And we want to find a longest subsequence that is common to both of them, okay? And one of the key word here is okay, we want to find one, okay, and it is not necessary because you could have like many longest common subsequences, okay. They are different, but they have the same length, okay. So you just need to, you are asked to find just one, okay. For example, okay, say X is this sequence, Y is this sequence. Okay? So what is the longest common subsequence? So we know B appear here. Okay, if we want to pick a D, then D will go here, right? And then the next one will be, so will be B, D, A, B, right? B, D, A, B. We have a B, D, A, B here too, right? So this is one of the common subsequences, right? One of the common subsequences. Is it the longest one? Let's continue checking about that. Okay, so let's say we skip the BC AB. So BCAB seems to also be another common subsequences. Another common subsequence that have the same length 4, right? So can you find something? Can you find a common subsequence which has length 5? It doesn't look like so, right? So this is another one, BCBA. Okay, you can, in these two sequences, you can find many examples of common subsequences of length 4. So this is just one of them, right? This is just one of them. Okay, so we will abuse the notation a little bit. Okay, what do I mean? Okay, here I will define function LCS xy. I mean, this function obviously takes two like an argument, like a sequence arguments. Okay, and it will return the longest common subsequence, one of the longest common subsequence. So why do I say I'm going to abuse the notation? This looks like a functional notation, but it is really not a function. Why do I say that? Because when you define a function, okay, if you give a, if you provide like the argument, the output, the return value should always be unique. OK， 如果说是一个方程式哦，你给它那个你 input 给好以后，它输出一定是固定的，一定只有一个。However, remember what I just told you? OK， 我们说这个the longest common subsequences between these two sequences. I mean, there are many examples. I just gave you two, right? And this is the third one, B, C, B, A. And no, they are all different, right? They are all different. But so this function, it is supposed to give you, one of the output, one of the longest common subsequences. But remember, I just told you this is not unique, right? 就是这个不是唯一的嘛，对不对？所以用 function 来写这个其实是有点问题的。 所以 that's why I say I'm abusing the function notation here. Okay, this is really not a function. Okay, but bear with me. Okay, please remember this something that looks like a function that's going to return you one of the common longest subsequence. Okay? Okay. So how to do it? How to do this problem? Of course, like we could do it like you know, the simplest way. I mean, brute force. Meaning, we check all the possible match, all the possible matches. Okay. So basically, okay, you know, we check every subsequence of one of them to see if it is also a subsequence of the other sequence. Okay, so how many subsequences you can create from one argument, from one sequence? 我先问你们，给定一个 sequence， 你要找到它的所有的 subsequences， 你要怎么做 ？How to do that？ 咦，这理论上应该蛮简单的啊。排列组合学过嘛，对不对？排列组合学过。Okay, it's a high school math. So basically, each character. Let's assume the simplest situation. I mean, of course, like if you when you look at this, you know, each character they could be the same. That's true. That's true. But let's consider the simplest situation. Every character in this sequence is different. 好，我们现在先假设每一个 character， 每一个字哦都不一样。那 then I'm asking you, okay, if you have like a such situation, like say every character is different, and you have m characters, how many subsequences you can create? 还是不知道？应该知道吧？就每一个 sequence 每一个 character， 你可以选或不选嘛，对不对？选不选，选不选，选不选。So totally, you are looking at 2 to the power of m, right? So there are 2 to the power of m subsequences you could create, right? So so you have 2 to the power of m subsequences out of x, okay? And for each given subsequence, okay, you just compare that with your y, okay, just scan through y and look at your fixed subsequence. Check if that subsequence will appear in y or not, right? So that's a quick decision, right? The worst case scenario, you have to scan through the y completely to verify that. So each checking takes big O(n), and you have 2 to the power of m subsequences, okay, out of x. So total time complex is going to be n times 2 to the power of m. Okay, so if you are a little smarter, you will say, oh, then this is obviously a big number, right? So you say, oh, let's try to, because this n times 2 to the power of m is a big number. So you may ask, okay, let's try to use if n and m are different. If n and m are different, obviously, like you would prefer to put the smaller one in the exponent, right? And the larger one like here. So if m is larger than n, so you'll use like m times 2 to the power of n, something like that. But regardless, okay, either m times 2 to the power of n or n times 2 to the power of m, okay, you are looking at exponential complexity here, right? Okay, it's, no matter which case we are talking about, it's always like exponential. So this is bad. Okay, this is bad. Okay. So is there a better way to solve this problem? Okay. So when we want to design a better algorithm, you will always try to abstract the problem a little bit, okay, such that you can create a recursive formula or recursion, okay, to better grasp like the concept. For example, okay, we can look at the length, okay, instead of look at the what the longest common subsequence is. Okay, let's focus on the length of the longest common subsequence. Or let's not even look at the longest. Let's skip the word longest. Okay, let's just focus on the length of a common subsequence. Okay, if you have something like that, you can extend. Okay, what do I mean here? Okay, let's first, okay, define, okay, the length of a sequence. S, say S is a sequence. Then the absolute value of S will be the length of sequence S. Is that okay? This is just a notation, right? Okay. 事实上，in fact, this notation has been used, I mean, in many textbooks, okay, that like absolute value of a sequence represent its length. This is very common, especially like in formal like a theory of computation, okay, 计算理论, okay. But anyway, like we are not in. I mean, I sometimes also teach this course, okay. But anyway, let's just want you to understand. So strategy. So let's consider prefixes of x and y. Okay, prefixes of x and y. Do you know the term prefixes? What is prefix? 就是前面的啦，从那个不知道中文要怎么讲，从开头到某个字，这叫什么？中文叫什么？就是前面的部分，一个字串前面的部分，这叫什么？中文要怎么讲比较好 ？Sorry 哦。My Chinese is poor, okay. Although my English is not that good either, okay. 我英文也没那么好啦，只不过说因为那个就是中文比较烂 ，OK. 那这个要怎么讲？这个是一个字串，你前面的从开头到这边到某一个点，这叫什么？前缀是不是？前缀 ，OK， 前缀。那当然有前缀，当然有后缀哦。就是从某个点到最后面，这叫 postfix, okay, postfix, okay. But we are not using postfix here. We are just going to be using the prefix. Okay, let's define Cij to be the longest common subsequence of the x from 1 to I, y from 1 to j, okay, their longest common subsequence. Okay, and then you get the length. 这样可以吗？就是他们的两个的前缀。OK， 从1到 I， 另外一个从1到 J， 然后他们最长的那个共同的这个 subsequence 的长度，我们定义这个东西。OK，so obviously the thing 我们最终要的是这个东西，对不对？就是 CMN 啊，对不对？CMN 就是我们要的嘛，因为 x 长度是那个是 n 嘛，那 y 的长度是 n， 对不对？所以说，如果你取 prefix 从1到 n， 是不是就等于说你取了整个的 x， 对不对？没有问题吧 ？OK， 好，同样道理 ，y 取到那个 prefix 取到 n 的话，就是整个 y。OK，so CMN is actually the longest common subsequence of x and y, and of course we are talking about the length. So we put an absolute. So far so good, right? 到这边还好吧 ？OK， 好。Then it will you will see this recursive formula. It's very, very beautiful. And let me tell you, any dynamic programming problem has something like that. OK， 所有的 dynamic programming 的问题都可以给一个 recursive 的这样的东西。OK，so Cij. Okay, let's look at the last character. The last character, like the i's character in x and the j's character in y. If they are the same, then the longest common subsequence, the length of longest common subsequence, okay, of x from 1 to I, y from 1 to j would be, cx from 1 to I minus 1, y index from 1 to j minus 1, okay? The length of that, the longest common subsequence of this, plus 1, right? Right? If they are the same. How about if they are different? If they are different, okay, then the Cij must be the larger one of these two, right? Either Ci minus 1j or Cij minus 1, and the larger one of these two. So you put a max there, right? Right? And that's it. So this recursion is kind of simple, right? Once you understand it, okay? I mean, it captures the essence of this LCS problem very, very beautifully. Okay? And pretty much any dynamic programming problem, you have to first come out with a recursion like this. Okay? So now you have a recursion, right? You have a recursion. So, because you have learned the divide and conquer, right? You have learned the divide and conquer. You will say, oh, that's easy. Let's just write a recursive algorithm that directly solve this problem. Okay. So this is a proof, but I think the proof is pretty straightforward. If they are the same, the rest is not important because we only care about this part and this part. So if they are the same, then it will be the longest common subsequent from here and here, plus one that comes from here. Okay? If they are different, then, so this is like a pretty straightforward. So I don't think like, once you look at this formula, recursion, I mean, if you can understand this formula, the proof is really a given. So I will skip this proof, okay? I mean, for those of you who are really interested, like in formal proof, you can go through this proof and just to get you used to this formality of the proof. But honestly speaking, this proof is just like to formally describe like what you understand from this recursion. Okay, it's pretty straightforward. Okay? So, in dynamic programming, okay, you will see what we call optimal substructure. An optimal solution to a problem, okay, contains optimal solutions to subproblems. Okay, what is the subproblem that we are talking about? We are talking about the LCS x and y contains like the LCS of prefix of x, prefix of y. Okay, so that's like the concept here, and this appear in dynamic programming. This also appear in greedy algorithm. So what's the difference? Yeah, we will talk about greedy algorithm later. Okay. So if z equal to LCS xy, then any prefix of z is an LCS of prefix of x and the prefix of y. That's what I meant here. Right? So, as I said, okay, once you have a recursive formula, okay, recursion, I mean, you can easily create a recursive program that solves the problem, right? Ideally speaking, yes. That's totally true. Okay, so it's going to be something like that. LCS xy. Okay, let's ignore the base cases because this is not our final answer anyway. Okay, we just write it just so that you understand this is a wrong solution. Okay, so yeah, I mean there are base cases. For example, when like you reach like zero, okay, if your sequence length reach 0, okay, then you need to stop, right? That's the base cases, right? So, but let's forget about that. That's, so if x equal to y, xi equal to yj, then cij equal to this one. Else, cij equal to max of this and this. Okay, so this is a very simple recursion. We just return cij. So this is a very, very authentic, okay, I mean, literal translation of your recursive formula, okay, into a very simple, pseudocode. So yeah, that's cool, okay? But let's look at how bad or how good this algorithm, the type complexity of this algorithm, okay? Because it's a recursion, right? So let's just take a look, okay? The worst case happen when xi and ij are different, right? Obviously, because, you know, when they are the same, like both I and j gets reduced to 1, reduced by 1, right? OK， 当这个 I 跟 xi 跟 yj 是一样的话，我们这两个 index 都同时减1，对不对 ？And in addition, we only have one recursive call when xi equal to yj, right? So that's the better situation. In a worse situation, it's like, you know, xi and yj are different. In that case, you know, these two index only gets to be subtracted to 1. Only one of them gets to be reduced. 就是 either I 减1或者 j 减1. And to make the situation worse, you have to make 2 recursive calls, right? 它不但这个降得比较慢，而且你有2个 recursive call， 不是1个。所以 it's obvious, like the worst case happen when xi and yj are different. Okay? So let's consider the worst case scenario, because when we analyze algorithm, okay, we always look at the worst case. So let's say n is 7, n is 6, okay? Assuming like the ending are always different. So we either go to 6, or 7, right? And 6, assuming the last characters are different. Okay, we go to 5, 6, 5. And so on, blah, 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 blah. So this is like a recursion tree, okay? You know, part of a recursion tree, because we haven't finished the whole thing, right? Just like the top 3, 4 layers, right? So from here, you can see that, wow, there's a lot of computations, right? There's a lot of computations. So the height is n plus n. Why? Because like, you know, you see each time, okay, we reduce m or n by 1, right? So if you want to reduce to base case, the base case is like both are 1 or both are 0, depending on how you define your base case, right? So let's say, like, let's define like a base case to be both are 0. So then the height will be obvious, because, you know, each time you reduce, go down by 1 level, you only get to reduce one of them by 1, right? So the height, obviously, like if you want to reduce both numbers to be 0, the height will be n plus n, right? Okay, and this is potentially exponential, right? Because each time you go down 1 layer, like you branch, like you know, the branch is doubled, right? The branch is doubled. So you are looking at 2 to the power of n plus n. So it's not any better than the brute force one, right? To be honest, it's not any better than the brute force, even though you have a better understanding of the problem, right? Because you understand the problem better, so now you have a recursion, right? And you use the recursion to write your program, and then the program looks bad. But there's a hope here, okay? We are solving subproblems that have already been solved. What do I mean? See here, this 6, 5, 6, 5. That this branch appear obviously twice, right? And remember, this 6, 5 represent like you want to find the LCS of x from 1 to 6, y from 1 to 5, right? So these two are identical. These two subtrees are actually identical, right? Right? And you can actually find a lot of identical stuff, okay? For example, if you expand a little bit further down there, like there are a lot of like repeated computations here and there, okay? So we want to do it better, okay? We don't want to repeat our computation, okay? Actually, okay, that's the key of dynamic programming. 就是 dynamic programming 重点就是说，它是一个 recursion， 但是它不希望去重复计算已经算过的东西。那 how do we do that? Okay, in a recursion, okay, we do it top down, right? So instead of doing this top down, because doing this top down, 你知道吗？你既然是那个就是 recursive call， 譬如说你 recursive call 这个跟 recursive call 这个，你不会知道说这个已经被做过了，对不对？对，因为你做 recursive call 的时候，这个跟这个是完全是它 branch 出去，它就完全不知道另外一边发生什么事情，对不对？对不对？这个是你如果你们大一学那个 recursive code， 你们应该知道这个东西，对不对？对，所以这是不好的。所以我们其实 dynamic programming 就是在做这个事，但是它是反过来做，从 bottom up。It do the problem in a reverse direction. So, dynamic programming hallmark number 2. Okay, a recursive solution contains, okay, if you do it like from top down, okay, then you will find in a recursion tree, okay, it contains a small number of distinct subproblems repeated many times. So you will see many subproblems gets computed like multiple times, okay, repeatedly. So this number of distinct LCS subproblems for two strings of length m and n, okay, notice that how many such subproblems exist? Because this is controlled. The number of distinct LCS subproblems is controlled by the index I and the j, right? 就是这个嘛。我们的定义，你看哦 ，Cij 每一个 Cij 是不是代表一个不一样的计算 LCS 你给你两个 sub 就是两个 sub prefix， 对不对？给你两个 prefix 计算它们的 LCS， 对不对 ？So this control how many possible subproblems we have out there, right? So how many possible I do you have? From 1 to m, right? I value range from 1 to m. J value range from 1 to n, right? So all the possible subproblems out there, they are only m times n, this many subproblems, right? But in a recursion, when you do this, you are computing much more number of subproblems, right? So what I'm telling you is that the number of subproblems is really not that big. It's really not that big. It's just m times n. So there are a lot of subproblems that, gets computed multiple times, because in here we compute the all the subproblems like exponential number of times. But actually the subproblem is obviously not exponential. Okay, it's not exponential. It's just like n times n. So we call such technique as memorization, but I would prefer to use the term bottom up. Okay, bottom up. But basically it means the same thing, okay? So after computing a solution to a subproblem, we are going to store it in a table. And the subsequent calls will check the table to avoid redoing the same work. Okay, this is very simple, right? You can say it's a memorization. You can say it's a bottom up. Why do I use bottom up term? Because we are going to do the subproblem from the simple one to complicated one. Okay, so LCS problem is going to become like this. So if Cij is nil, okay, then it means like it has no value yet. Okay, then we start this, because this is just a base case. Like we try to, or like this is like a border case. Okay, so if this one hasn't been assigned a value, then we start here. Okay, then if xi equal to yj, then we are going to Cij equal to, this part is the same. But here, okay, we want to do it in a table. But actually, this writing, I don't like it. I don't like it. Okay, this is still recursive code, but it's not exactly what we usually consider like dynamic programming is doing. Okay, but conceptually it's equivalent, but it's different. Okay, it's like this. Dynamic programming is about table filling. Okay, the better way to explain that is through a table. Okay, so this is like which one is X? A, B, C, I believe like, sorry, I forgot which one is A, X, which one is X? A, B, C, oh, so A, the one start with A is X. Okay, oh, shoot. So this one is X, this one is Y. Okay, and then we, and obviously, okay, there's like a what should I say, like the boundary where like the prefix of length 0, so it's a 0. We have like a prefix of length 0. So the table size is pretty much n plus 1 times n plus 1, right? N plus 1 times n plus 1. Okay, and then, okay, you fill 0 for boundary case, where, here it just means like the prefix 0, okay, nothing here. So this one just A and, well, for B it's an empty string. So obviously, like it's a 0. So this number represents the size, the length of the longest common subsequence, okay, of two prefixes, okay. So we can fill out this line, this row and this column easily, right? And then, okay, we try to construct, okay, this table, you know, as I say, bottom up. Okay, what do I mean? Okay, if you look at here, for example, this is A, B, right? Because A, B are different. So you try to, because A, B are different. A, B are different, okay? The Xi and Yj are different. So you try to get the max of one of these. So you get like, you know, A, B are different. So you get like the max one of this one and this one. So which is 0, right? Because both are 0, okay? And then here, okay, you try to find like the AB and the B, okay, here for this one. Because B and B are the same, right? So it's going to be, you know, the Ci minus 1, J minus 1, plus 1. So it's going to be 0 plus 1. So it's this one, right? So you can see that you can fill out the table easily, right? So each blank filling takes constant time, right? As long as you construct from smaller instance to a large instance. That's pretty easy, right? I mean, you can do it like in row major or column major. It doesn't matter. Okay? 你要一个 row 一个 row 去 fill， 或一个 column 一个 column fill 都可以。OK， 那个概念就是你就是用这个嘛。如果它们是一样，就是它们的斜对角线加1。如果不一样，就是说你看上面跟左边的两个的最大的那个填过来。OK，so because each blank filling take constant time and it's like n times n plus 1 times n plus 1, so it's complex is n, big O m n. So at the end, the longest common subsequence is 4. Okay? Well, actually, I'm you know, exceeding like 现在已经10点了。我们 let's take a break. Okay, when we come back, I will continue. Okay.